Hello everyone. So my name is Tao Tan. Welcome to our IEEE EMB's webinar. So today we are pleased to have Dr. Zitong Yu from Great Bay University with us. Dr. Yu has a very strong background in computer vision. So before his current position, he has conducted research at the University of Oulu, NTU, and Oxford. His work is well recognized in our community for the high quality. He has consistently published in top journals like TPAMI and top conferences like CVPR, IJCV. So beyond his research, he also serves the community as a consulting associate editor for IEEE TIFS. So today he will share his insight on video-based remote physiological measurement. So Dr. Yu, thank you for joining us. So the floor is yours. Please get started.
Okay, thank you, Professor Tom, and thank you, IEEE EMBS. I will share my screen now. Okay. I hope everyone can see my screen, right? Okay. So, how to? Okay. Hmm. Sorry, I stop here. Okay, I share again. Okay. Okay. I will start now. Okay.
Yes, we can see the screen. Yes.
Okay. I'm Zitong. I'm from Great Bay University, and today my topic is about seeing the heartbeat, video-based remote physiological measurement. At first, I will show my outline of today's talk. I will introduce what is RPG first, and introduce some classical methods for RPG measurement, and introduce some extensions of RPG, and finally we do the summarize and proposed. And first, what is the RPG? If you can see the the figure in the middle of this page, if we show a maybe a light source, and the light source will reflect by the skin, and some lights will go through in the skin and reflect back through the bulb based on the bulb vessel. And for the camera sensor, it will receive a partial of the diffuse refraction and spectral refraction, and we can measure based on the color change of some diffuse reflection, and we can get the RPG signal based on the subtle skin color change from the human surface. And finally, we can estimate some vital sign, for example, heart rate and blood pressure from the RPG signal. And then let's see a vivid demo about what is the RPG. If we get a region of interest from this phase region, and we do the average pooling of each friend, we can get an RPG signal like this. Uh, if we use some, for example, in this ACM TOG paper, we do some color magnification, and if we apply on the face surface, we can see the green color and the red color periodically, and this is the magnified RPG signal. But what is how it apply into our daily life? For example, it can use for some driver state assessment or some healthcare. For example, the some heart disease detection, and also can detect some face attack, and also can be used in our consumer electronics, for example, AR glasses. And it will influence as the signal, every signal is very subtle, and it will easily influenced by the head motion, illumination, and video quality, especially for the video compression, and also it will measured very for the biased skin color, for example, the black color. And also for the female, the sun makeup will influence the RPG signal measurement. Next, we will introduce some classical methods for RPG. This is an overview of the RPG signal method. I just list some classical methods inside, but not limited to all important methods are included. For example, the first RPG paper published in 2008, and it can be in this paper they find some RPG signal can be measured from some animals and human, and after that. They want to use this technique based on the human face and other reasons. But mostly in today's talk, we will use face reason for RPG measurement. And after 2008, there are several years for the traditional signal processing methods for RPG measurement. For example, using the ICA or PCA or some color space transform, for example, Chrome, POS, and 2SR and LGI. For the all these methods are based on bright source separation and some color space signal processing. Yeah, they don't use any data for learning for modeling. Yeah, and after the 2018, the first end-to-end CM methods called deep physics developed by the MIT. He designed use 2D CNN for the heart rate estimation, and after that, there are several 3D CNN based methods. For example, the FISNet and FISFORMA or efficient physics for the RPG measurement. They will leverage the rich spatial temporal information for the robust RPG measurement. And besides this end-to-end method, there are few groups also use some spatial temporal map called ST map for the RPG estimate. All these methods are based on labeled data supervised learning. And recently, there are several methods, for example, contrast SIMC or RPG MAE. They use unlabeled data for the self-supervised learning, which also is a very promising direction. And recently, also some new method based on the large language model, and but not least in this milestone. Let's introduce them step by step. For the first paper, I mentioned previously in 2008. In this paper, they find different skin region. For example, the forehead and the hair, or the other skin region. For example, their hands. Yeah, they have different intensity of the RPG signal. For example, we can find a very clean, related clean RPG signal from this blue region, this forehead. But if we find in the hair region, this is very noisy. And if we see the black region, the whole picture, whole figure, it will also contain some RPG signal, but it's also very noisy. And beside the region, they also find that from the color space, the green, red, blue, green, the green channel is the most sensitive to change in broad volume. And after it, many signal processing and blind source decomposition method, for example, the ICA method developed. They usually separate the noisy signal into different components, and they find maybe most periodic component. They think this is the trustworthy RPG signal. And this is also a very classical paper, because this is the first time to measure it in some realistic situation. what is a realistic situation? In this paper, they define with changing illumination and with some large head motion or expression. They think it is a realistic situation. How to solve this issue? This is pipeline. First, he detect the face and check the RI region based on the facial landmark. And after that, they use some least mean square filter to remove the background light illumination from the face region. So they can get a clear RPG signal beside the noise, except the background noise. And after that, they select the most traverse clip without very sharp motion, head motion. For example, they estimate the motion and they think the phase 2 with sharp motion. So they remove this signal part and then they combine the signal from phase 1 and phase 3 together. So they get this is a new signal. So this is a very handcraft pipeline, and it will easily to overfit. I mean, not data-driven overfit into this data set simulation. For example, if we change to another environment, maybe this step or this step, they work badly. So after that, there are so many end-to-end supervised learning methods to derive for measure RPG. What is end-to-end? We can see for the input, we have a facial video, and we want to model some spatial temporal level or the spatial level or temporal level. They can directly estimate the RPG signal using our model. So how to decide these spatial temporal networks? In this BMVC paper, we first investigate two kinds of spatial temporal network. The first one is based on the 3D CNN. Use some 3D convolution to filter out spatial and temporal noise, and they can learn more spatial temporal intact context. And another one is using the 2D CNN first, and they use the RNN-based temporal recurrent modeling for the temporal signal estimation. And we find that using the 3D CNN, the estimation will be more robust. And after that, we also try to use the transformer architecture to help to capture the long distance temporal modeling. For example, we design a temporal difference multi-head self-attention model. What is our contribution? In one side, we design a temporal difference convolution, which can enhance the local spatial temporal RPG information. And after that, after we insert the TDC into the Q and the K projection, we can get a more reliable attention map. And after that, we can get the better attention performance. If we remove this TDC, just use the multi-head self-attention, this attention map will be very noisy. And after maybe a layer multi-head self-attention, it will very hard to converge. And then what is the TDC? We assume that we want to enhance the local spatial temporal color change. So we do the difference between the local spatial region and the adjacent friends regions. For example, this CDC temporal. The red one is the current feature, and we duplicate it into the last friend and future friend, and they do the difference. And then we get the difference map, and then we calculate the 3D convolution based on this gradient map. And we can see the feature map from using different convolution. For example, the linear 3D convolution and the temporal different convolution. We can find that our proposed convolution can capture more reliable dynamics. For example, the hand trajectory. And we also apply this TDC into the member architecture. Also, we insert the TDC before the by member, and it can also enhance their local spatial temporal representation. And besides the using the video input for the end-to-end training, some group they also divide the spatial temporal map as the map, and they use this map as the input to the CNN for supervised training. So what is the estimap? In the this TIP paper, they first proposed this spatial temporal map. First, he do the face detection for the face region, and after that they divide the face region into n by n blocks, and they can get n blocks, and for each blocks they will do the average pooling, and they can get the n n n RPG signals, which signal is transferred into the YUV color space. So they can get a spatial temporal map. For example, this x axis is the the time, and this vertical axis is the n block. So they can get this spatial temporal map, and they will use this estimate as input to the, for example, ResNet to do the heart rate estimation, and this map also have several noise regions. For example, this maybe the region from this eyes or the region from this background, they don't have rich RPG signals. So they improve this spatial temporal with the multi-scale space. And they define some RI region from the face region, and use different kind of combination of the face region, generate different kind of signal. And each signal they with RGB and YUV color channels. So they finally get a very complex multi-scale estimate, and they can estimate more reliable results. And recently, some work also used the vision language model and the large language model. For example, this PhysLM. The motivation is that they assume that only use the video encoder. It is hard to perceptive the current environment. For example, how this human their attributes, and how the environment attribute, and how the signal, the quality of signal looks like. So at first, besides doing the visual encoder, they also use the pre-trained, for example, some DISIC or some other lava, some well-known VRM model. They ask them some a question about the task. For example, how this subject look like, and also they will ask them some question about the vision cues. What is the environment? What is the domain? The human standing. And also they will ask some static cues. A static is about the signal level there. What is the signal distribution look like? And they will put these three kind of task cue into a depth prompt learning model. This is they will use the data to learn how to fuse these three kind of cube. And besides this task cube, we also get the fusion feature from the fusion encoder, and we also get the cost RPG estimation and get the RPG cost RPG distribution statics. And we put these three kinds of feature into the large language model and do the LoRa Python. And finally, we do the prediction. In this framework, we can, even though we cross-testing in the unseen domain, we can still get some very rich knowledge about this new target domain, and so that they can generalize better. And besides the supervised learning method, there are some recently there are some methods they learning without label. As the reason is that the current RPG data set they are very small scale due to the very high cost to collect large scale label data, because they should measure their using some contactable sensors to measure this ground truth is very time costing and inconvenient. And this is the contrast phase. This is very classical unsupervised RPG learning method. They based on two prior knowledge. One is the spatial similarity. They assume that different facial region they will keep the similar Ph.D distribution. For example, they divide into A, B, C, D four region. They assume that the RPG from these four region they will share the similar frequency distribution. And another one is the temporal similarity. For example, they assume that the the nearby temporal clip, they will usually share the similar heart rate distribution. But this is not very accurate. For example, in some sport or some fitness scenario, their heart rate will change differently in the even though in the successive windows. But in most data set, they will just a static scenario. So they do experiment in this scenario, it will be fine. Okay. And then what is contrastive learning? Based on these two prior knowledge, they will do some augmentation. For example, different spatial region augmentation, and do a different window sampling. So they will get for two subject video, they will get different kind of augmentation signal, right? And they will estimate their Ph.D distribution for different signal. They will attract the video, the Ph.D distribution from the same subject, and they will repel them from different subjects. And besides the constructive learning, there's some group from the University of London, and they based on some periodicity and some a limited bandwidth knowledge. For example, the heart rate, the normal from the normal subject, they usually range from 40 BPM to 180 BPM. So giving a batch size of video, they will get a batch size of RPG prediction and their Ph.D distribution. So they will force the distribution um, have the focus on the bandwidth from 40 to 180 and make it sparsity from the other region. So we think that we have a regularization loss function to make this signal have higher SMR, signal noise ratio. And beside this loss function, they also assume that the batch size, the batch size variance should be large, so that they will not converge to a very overfit to the specific heart rate. For example, the normal heart rate usually range from 70 to 80. So if we don't with this variance, the model usually they overfit to very limited BPM values. Another, besides the contrast learning and the directly constraint learning, we also devise some model based on the mass autoencoder for unsupervised learning. In this method, we first extract the estimate map from the face video, and we do some ROI regions, randomly mask some ROI region, and we want to reconstruct the complete ST map. And after this reconstruction, we know that some dynamic or periodic region, how they connect with some seen region and the unseen region. So we think that from this self-supervised learning, the model know what is the periodic RPG looks like in the ST map. So after with this pre-training, we just use several very few short fine tuning. We can get a very promising result. And we also benchmark some semi-supervised learning benchmark. And we also think that if we have limited label data, but we have large-scale unsupervised data, we can combine them together using some pseudo-labeling strategy. And for the video quality enhancement issue, we also propose a two-stage framework. For example, first we enhance the video quality based on some spatial temporal video enhancement network, and after that we predict RPG signal based on this enhanced video, and then we train this network jointly based on the reconstruct loss and our RPG loss, so that the reconstruct video they will have rich RPG cues. This is a demo of our algorithm. We can see that after the video enhancement network, our predict curve see the blue curve with more similar trend from the ground truth ECG. And also there is some elimination method, especially in the driving environment. So in this paper, they also use a two branch algorithm. One branch is based on the face region, and another branch is based on the another background region from the car in the car background. They also do some constructive learning to force the face region feature they should attract together, and with the background region or the interference feature, they will appear then far away. And after the classical methods introduction, we quickly introduce some extension of RPG methods. Besides the face region, some research also extended from the whole body region. For example, the the hand and for the leg, and also for the leg, they will find that they will have uh, uh, some transmission time delay from different regions. So it's hard to train on facial data and generalize well, transfer well into other skin region. But this is interesting. We can use the face difference from different region to maybe measure some different kind of disease. And another interesting direction is for the process editing, because our RPG data is limited. Another direction is how to generate our new RPG data, right, using the original video. In this work, they first estimate also the estimate and they do some signal detriment and giving a target signal. They do some similarity optimization so they can get some very subtle perturbation signal, and after that using this signal back to our only skin region so they can get the edited video. Looks very similar to our original video, but they have perturbation signal only on the face region. After that, also some VAE-based encoder, decoder, and also diffusion based method for the face editing. And also in this diffuse, they also modeling the ground truth noise and our facial features jointly to our spatial temporal hybrid denoiser. And interesting is that different from the original diffusion modeling, only use the noising signal for the input. They disentangle this noisy RPG signal into the trend perspective and the amplitude perspective. Seen from this knowledge, they think the trend, they will measure how the PPG signal looks like, and the amplitude measure how the intensity of the RPG signal in different region. And for the inference of this physics diffuse, they also sampling with different kinds of RPG sample and choose the most reliable. For example, they measure different windows from this signal, and they use the majority voting, use the most similarity of the Ph.D, and they think this signal is more reliable. So they use this output as their final result. And another interesting direction is using the personalization and the test time adaptation. This is a good solution for overcome the domain shift issue. For example, we train a RPG model first, and but for a new subject, they will only do the weight update using only one sample of this new subject or new domain environment. And another solution is use TTA for each sample from the each subject and each domain. They will turn it sample wise. They will get a more accurate result. And we also introduced some applications. For example, the AF detection. AF detection is look like this. This is a healthy subject. Their ECG wave is very periodic and regular. For the AF disease, they will looks like very irregular distribution. For example, we can see this part and this part. They will look very different from this part. So we can also use RPG technique to detect this AF phenomenon. And we can also use the RPG for some affective computing. For example, for the pen estimation. The classical pen estimation from the video is using this button brand. But we can also use RPG brand for some information guidance, and they can get the better pen classification result. Finally, we also find that the RPG can use for do some face attack detection, for example, anti-spoofing and defect detection. If we look from this, the first row is real face, and the second row is mass attack. And if you use some appearance information, for example, the textual information is very hard to modeling the difference between the real face and the 3D mass attack. But if we extract the RPG signal from the real face, we can get the estimate from this row. And if we get the RPG from the 3D mass attack, we will see a very noisy estimate. So we can predict how real face and what is the 3D mass attack from using these two kinds of estimate. Finally, we will give some summarize and prospect. The first one is the generalization issue. For the RPG method, because the signal is very subtle, so it's very challenging to do this kind of, for example, subject difference, motion, lighting, and video quality. And we can use some sensor, for example, multi-modal sensor, imaging sensor, for example, using MRI or using IF sensor to enhance the generalization issue, but it will increase some customer device cost. And we, besides the hardware, we want to also measure some other parameters like SpO2 and blood pressure. And also we want to develop more advanced architecture and make the architecture more efficient. And we also want to apply it into more applications. And the privacy issue is also important for the face analysis. And finally, we thanks to some collaborator and my previous supervisor, and also thanks to the members of my group. Thank you. This is my email. If you are interested to cooperate and ask questions, please send me an email. Okay, thank you.
Okay,
Okay.
great. So Camila, I see a few questions from the audience. Should I pass it to Professor Yu?
Yes. Could you please probably read the questions?
Let me read the questions. So, Professor Yu, the first question is regarding multimodal fusion. So, do you think incorporating multimodal sensing, such as multispectral imaging or depth camera with access to richer physiological cues, right, like blood pressure surrogates, can fundamentally improve the robustness of remote physiological measurement models? In your view, what are the most promising ways to exploit the complementary strengths of these modalities without significantly increasing acquisition complexity?
In my view is that we can find the because if you use different type of models modality, right, we will have many redundant features or information, because for example some information already have very high certainty in the RGB, and some already in the maybe NI. So how to select the non-redundant features or token from different modality and fuse it, it will increase the efficiency and maybe enhance the maybe our fusion performance. Yeah, this is my view. Thank you. Yeah.
Okay, thank you. The second question on cross-modal temporal alignment, different modalities. Um, okay, different modalities often operate at different sampling rates and may introduce modality-specific latency. So, what strategies do you consider most effective for achieving reliable temporal alignment in multimodal physiological measurement? For example, adaptive synchronization, learned alignment, or cross-modal transformers.
Yeah, yeah. The alignment problem not only in the multimodal issue, I think, even though for in the in different only in RGB modality, right? Different data set, maybe some using the camera with the 30 FPS, high speed camera, for example, 100 SPS, they also have this problem. One solution is that we do the alignment before the sending in the new level, right? We do it using some signal processing method to align previously. This is one solution. If we input then different different sampling rate to the new level directly. Another solution is that we use some maybe temporal maybe model to maybe modulate automatic adaptively maybe use some new maybe strategies, right? This is depending what your architecture like. I believe nowadays some temporal modeling model can overcome this issue. Yeah, thank you.
Okay, thank you. So the third question is on real-world illumination noise. So most existing datasets are collected under relatively clean and controlled lighting, right? Whereas real-world environments contain dirty illumination sources. So in practice, we found that even highly accurate ROI extraction or skin mask segmentation, illumination artifacts remain a dominant source of error. So for your perspective, what modeling or system level strategies beyond the conventional pre-processing are most promising for fundamentally mitigating of those illumination disturbance in real-time deployment?
I think we can use some training data, right? They have the normal illumination and also with very dirty illumination, right? And we can use some normal illumination feature to guidance the dirty one, and so that we can use this distillation maybe algorithm to let our model to learn how they transfer knowledge from normal to maybe abnormal illumination. So I think this will be generous well only using some normal data or abnormal data. Yeah, this is my view. Thank you. Yeah.
Okay, so this is mainly for training. So another following question from another audience is that when we move RPPG method to real clinical scenarios with strong motion, again, illumination changes and diverse population. So do you see larger gain from architecture design or from data-centric strategy like multi-domain dataset design and strong augmentations? So
I
which one
think
is better? Yeah.
yeah, I think the architecture is the basic, right? Because we find that if we use different architecture, we even though in the same benchmark, their performance will vary a lot, right? But if we keep the same architecture, right, after that we the some augmentation algorithm and the learning algorithm they should be designed well, right? But I think the architecture is first, and after that we choose the maybe correct augmentation strategy. Yeah, this is my view. Yeah.
Okay, thanks. Another question from myself is that, so in medical imaging field, right, we see lots of foundation model in pathological images, radiological images, ultrasound images. In this RPPG field, do you think is any way to build a foundation model?
Yeah, it is many group. I think, for example, also in your group, right? Some CVPR and our group ChaLearn. Also maybe tries towards this direction, right? But the limitation is the data size, right? I think these two way to do these things. One is use the AIGC technique to maybe generate some large-scale data, right? Another way is using some semi-supervised learning, use large-scale unsupervised data. But as you say, many unsupervised data is very noisy, right? They maybe it's not easy to learn these subtle RPG data sets. So I think the most possible solution is that we collect large scale of RPG data from different kind of clinic for example, hospital or different kind of maybe our home or daily data. We combine these different kinds of situation data together to train a foundation model. I believe maybe in the coming years we will achieve this. Yeah, thank you.
Okay, thank you. Yuan Kai, Camilla, I don't think we have more questions here.
Yeah, let me see. Yeah, if the audience have any questions, please ask a question into the Q&A. Okay. Yeah, I do have a question. Yeah, so you mentioned that the data augmentation may increase the generalizability of the model for the real-world images. Do you think we actually need the real-world scenarios for this technology, or the lab setup is good enough?
I think we really need a real world scenario, even though for some few short samples from real world scenario. As we know, if we only use the lab data, we do the cross testing, their performance is very poor. Yeah, even though in another lab scenario. Yeah, so actually we need the real world data. Yeah.
Great. Okay, great. Seems there is no more questions in the Q&A. And that was a really great talk, Professor Yu, and thank you so much for your time and your exciting talk. And let's keep in touch offline if any audience have more questions. I think that's today's webinar. Also, thanks so much, Professor Ken, to organize this webinar. So this has been a really great one.